All right, hello and welcome to today's webinar. This is the third and final session in the 2023 Kenji Ishihara Colloquium, hosted by EERI's San Diego Regional Chapter. My name is Elizabeth Angel. I'm EERI's Communications and Program Manager. And before we get started today, I just want to take a brief moment to mention EERI for those of you who aren't familiar with the organization. The Earthquake Engineering Research Institute is the leading nonprofit membership organization that brings together professionals from a wide range of disciplines, both in the US and around the world, who are working together to better understand earthquake risk and increase earthquake resilience in our communities. You can find out more about EERI at our website, and that link there at the bottom of the screen will show you how to join us and talk about the benefits you get from being a member. And these webinars are just one of the many activities we do. So I hope you'll look into this and think about becoming part of the organization if you're not already. I also wanted to just briefly mention our 2024 annual meeting that's coming up in Seattle next April. Registration is now open. You can use that QR code or follow that link to the website. And we're going to have a really great menu of sessions in the technical program, including some that deal particularly with the impact of these earthquakes and the reconnaissance that you'll hear about in this session, as well as a lot of other great activities, workshops, the seismic design competition. There will be a full day reconnaissance field exercise based on a Seattle Fault 7.0 earthquake scenario that we're going to host with the Washington Geological Survey. So check out the website to learn more, and we hope to see you in Seattle next year. And with that, I'll turn it over to Hamid and Gloria from the San Diego chapter, who are going to be our moderators today.
Thank you, Elizabeth. Hello, everybody. We are very happy having the third day of the Ishihara Colloquium in 2023. For today, we have three wonderful speakers. We have Louise Comfort, Professor Emerita of University of Pittsburgh, where we will host Keith Miyamoto, founder and CEO of Miyamoto International, and we're gonna host Ezra Rampouli, Senior Managing Engineer in Exponent. I also have my friend and colleague, Gloria Ferrone, Assistant Professor of San Diego State University with me. Gloria, please.
Thank you so much, everybody, for joining today for this last colloquium series. Our first speaker is Louise Comfort.
Hello, everyone. Delighted to be here. Well, I'm really, first of all, my background is public policy, and as a social scientist, I'm really interested in what happens to the communities. And we have an extraordinary situation in Turkey where we've got an old problem, which is the discrepancy between knowledge and action. And it was very vividly evident in the February earthquakes in Turkey. And this earthquake, or this dilemma, is really one where there is known risk, but failure to act, which leads to recurring disaster. And in Turkey, 6th of February, two very severe earthquakes occurred within one day in the same region, causing enormous loss. The president of Turkey at the time, Erdogan, said it is not possible to prepare for such a disaster. In fact, in EERI and in many disciplines across the world, a whole lot of professionals spend an awful lot of time thinking about this. So the question is this assertion valid, given the knowledge, resources, and skills that are available in contemporary Turkey? And consequently, we did a quick response study to explore the possible strategies for managing known risk. So the goal of the reconnaissance study was a quick response study actually funded through the Natural Hazard Center at the University of Colorado under an NSF grant. And the goal of a quick response study is really to identify the major issues, and given my background for social science research, that were generated by these devastating events of the 6th of February in Turkey. And the primary focus of the team was really to focus on the communication and coordination processes that were in place before, during, and after the question. And the reason for communication and coordination is this is essential for learning. If there is a lively process of communication, it allows coordination in Turkey. And was this up and running in Turkey? Our primary methods for social scientists essentially were 3: semi-structured interviews, direct field operations, and documentary review. And the key issues we were looking at were, what is the socioeconomic and political context? What were the consequences of the collapsed housing and how that triggered internal migration within Turkey? And what was the psychosocial trauma in the damaged cities and the impact on schools and uses of technology? So our field study, very brief, literally 8 days, March 4 through 12. And we spent 2 days in Ankara, where we interviewed first Turkish experts in public administration, earthquake engineering, psychosocial trauma, business administration, humanitarian assistance, before we went to the field. Then we had 3 days in the field where we were actually interviewing field managers and also, walking through the disaster sites and locations and visiting the field operations, observing field operations in process. And then I spent a final day in Istanbul with interviews with Turkish experts in earthquake engineering and seismology. So going back to the question, is it possible for people to learn? If we look at the context of Turkey on February 5th, 2023, we have a situation where there's known seismic risk in the country. The major earthquake faults have been mapped. There have been major changes in policies, building codes, and disaster planning enacted since the 1999 earthquakes in Kocaeli and Düzce. And we also see Turkey is a middle income country. It is not at the bottom level of poverty, but it has been characterized by rapid urbanization in the last 30 years. And the primary driver of economic growth has been the construction industry. And the question is, in this construction industry, did they follow all of the building codes that were enacted in 1999? Further, there's been a recent increase in inflation that has added to economic and social uncertainty. A third critical point emphasized by the psychologists that we discussed was that Turkey in February 5th, 2023, was really a fragmented society with deep political divisions, lack of trust, lack of communication within and between organizations, and institutions that were hollowed out by loyalty tests to the current government. Politically, difficult time. Presidential elections were scheduled for May, and the response to these devastating events were really colored by the election campaigns, rivalries, and very deep suspicions between the governing party and the opposition party. But interestingly, technologically, there were highly innovative uses of technology in response operations, use of drones for damage assessment, GIS for mapping of seismic risk, WhatsApp groups for rapid communication, and a mobile phone penetration in Turkey of 101%. Now, what happened? February 6th, we have the impact of these sudden severe earthquakes over a wide region, 11 provinces, 10 cities, many smaller districts in the region, over 13 million residents. And asking the experts about, did Turkey learn? To an expert, they said no. In fact, the changes that were designed and adopted after 1999 were not sustained, despite the knowledge, skills, and capacity to reduce seismic risk. The actions that had been initiated atrophied, and they were overridden by other priorities at enormous cost. Cost in losses in lives, over 50,000 fatalities in Turkey, and 115,000 injured in Turkey, over 8,000 in Syria, over 240,000 buildings that had been damaged, rendered unusable, and a cost of $103.6 billion US. So the challenge is how to rebuild, how to reestablish communities, how to reconnect families and neighborhoods in sustainable ways. Seismic risk remains in Turkey. The earthquakes will recur. And the question is, can people learn to live with seismic risk? So we were looking really for the major areas for social science research. In terms of communication, we found a real discrepancy between the technical capacity for electronic communication and the organizational capacity to manage accurate and reliable information exchange. And in the first 3 days after the earthquake, person after person reported that there was literally no communication in the damaged cities. So without communication, there can be no coordination. It fails. And indeed, what was reported were the first days after the earthquakes were chaotic. It was difficult to send help. It was difficult to receive help. And it was, of course, a crucial time for life-saving operations. And the failure then compounded the distrust and the anger at governmental operations. The consequence also led to the lack of shelter, and the collapse of housing led to internal migration of residents from the earthquake damaged region to other parts of Turkey. Over 3.5 million people literally left these areas and scattered across the country. And would the new housing that was promised by the president within 1 year be rebuilt? And most importantly, would it be built according to code, or would the disaster simply be recreated in another decade? And in the photographs, you see Turkcell. Turkcell was the one Turkish, there were essentially 3 Turkish communications companies, and one is Turkcell, and they will essentially build the infrastructure for cell communications across Turkey. And at the bottom photograph, you see the AFAD tents that were put up for shelter as people had lost their homes. Then other areas of social science research was psychosocial trauma, and the size and the scale of losses really fundamentally disrupted the sense of security and stability in whole communities. And here we see at the top, there was a psychosocial center that had been established. This is in Gulbasi. And at this center, there was this marvelous tent that was set up, and you see it in the photograph on the top left, with a playground for children, and in an effort to bring some brightness, some light back in. The other impact was on education. And also in a photograph, you see a tent school that had been set up because the earthquakes occurred at the critical time where students were preparing for their annual examinations. And in Turkey, these examinations are really critical from junior high school into high school, and from high school into college. And the placement on these exams really determine which high school you can attend, and which high school you attend determined which university you can attend. So these are very critical examinations, and this town of Gokasi was very concerned about their students and trying to maintain preparation for the exams. And the third major issue is the uses of technology. And what was interesting, and at the bottom photograph, you see this is a field operations center. It was actually a mobile center, but you see all of the technology that was there. People had their laptops, their iPads, major monitors in the background, streaming television coming in from different locations, access to different centers, information centers around the world. And so we do see a much more rapid increase in connectedness, but I'm sorry to say this came after the event, not during the event. And then we see the cascading effects of these earthquakes on recovery. And one of the most important and most critical areas of recovery is business operations, because when people scattered, what happened, first of all, they lost their businesses, they lost their homes. In the upper photo, you see the collapsed businesses. One, interestingly, a bottom business, is still standing. It's the businesses on top that collapsed. But the bottom of the photo sees what was all too common a site. This is a site in Gaziantep, and this is a city where parts of the city were damaged, heavily damaged, but parts were standing virtually intact. And here is a spice merchant with his very colorful spices hanging, and everything is in perfect order, but he is standing alone. There are no customers. And so this is a major issue. How do you rebuild? How do you maintain? How do you sustain a business if you have no customers? And so this becomes a dilemma for business. Do they stay open? Do they close and then reopen? Many of the businesses actually turned to online advertising, where they would ship things, but because transportation was down, shipping was also a problem. Then another area, and a very important area that we were interested in, was the role of nonprofit organizations, especially in public health. And surprisingly, we saw a limited role of nonprofit organizations. And usually in disasters, under the United Nations Charter, all 193 nations are obligated to support a nation that has suffered a major natural hazard event. And indeed, Turkey requested support for search and rescue operations. And 69 to 70 nations sent search and rescue teams, but very few other teams came in. Field hospitals were established by Turkey, and Japan indeed sent a medical team. But the major international NGOs, Save the Children, CARE, World Vision, were not visible and were not active. And it was interesting because while the international organizations were not encouraged by the government, the AFAD Turkish personnel said, wait a minute, with this disaster, we did not receive sufficient aid from the international community. So it again is this sense where, did the government actually want international agencies to come in, or would they be a burden? And was this in fact an issue of not getting sufficient aid to the people in the communities that needed it? So the challenge really in these complex urgent events, especially large-scale events like this one, is to align these decisions across the jurisdictions. And these are difficult circumstances in any case where time is short, the conditions are changing, information is incomplete, and operational personnel are compelled to act with whatever information they have available. So this is the tension for operational personnel. It's also the tension for agencies that are trying to assist, is how to remain open to new information that reduces the uncertainty, or do they assert control over known action, even if it's wrong, in order to act? So this is what we saw with the humanitarian organizations, or the search and rescue organizations came and were welcome, but the international humanitarian organizations were kept at bay. So what we recognize is that cognition structures action, and it helps to create this balance between openness and control, but that balance varies with the severity of the risk, the access to information, and the infrastructure of technology and organizational support that is available. So the whole task of transforming communities, collective trauma, into learning is a major task that we honestly don't understand very well. It is a collective process. No community can do it alone. But transformation, successful transformation, does depend on the support, the understanding, and the guidelines that are set by a wider institutional context of the traumatic event. So interestingly, in this earthquake, the UN guidelines were not altogether followed, and it had an effect, literally, on the communities that kept them in trauma longer. So one of the things that can be done ahead of time, of course, is to establish the connections for available resources, the financial, organizational, technical, emotional intelligence resources, and they're instrumental to the learning process. So these communities, if they receive the support that is necessary to rebuild, if housing can be rebuilt and communities can be recreated and businesses reestablished, people will heal. If that is not the case, the trauma remains. And so aligning the learning processes among different groups, and especially different jurisdictions, is fundamental to achieving a consensual goal in a dynamic social environment. And I very much want to acknowledge first my Turkish colleagues, Süleyman Çelik and Başak Süleyman Çelik is from Anadolu University. Başak Erkan is from Middle East Technical University. And they were absolutely indispensable colleagues who, of course, both are bilingual. They knew the areas, they had contacts, professional friends that really supported us. And this small study was supported by a quick response grant from the Natural Hazard Center, which was funded by the National Science Foundation. And of course, we want to acknowledge the Turkish colleagues who advised us and gave us contact information and supported us in the way, as well as the Turkish organizations whose personnel we interviewed. So thank you very much. That's my.
Thank you so much, Dr. Louise Comfort. Very appreciate your great lecture and talk. I want to just add a quick bio about Dr. Comfort. Dr. Comfort is a professor emerita and former director of Center of Disaster Management at the University of Pittsburgh, and she is a visiting researcher at CITRES of the UC Berkeley right now. If I want to continue about her, I need to continue for a few minutes just talking about her achievement, accomplishment, and awards. So, but I wanna, since I don't see, Gloria, any question at this point, until the end of the session, we also can take questions and answers. I have Dr. Comfort transfer them to Dr. Comfort. But now, luckily, we have Dr. Keith Miyamoto here joined us. So let's go with him. So I transfer it to Gloria for the bio of Dr. Miyamoto, and then we will have him. Thank you so much.
Okay, thank you so much. Please send us your questions for Dr. Comfort, and we will answer them after the presentations. It is my pleasure now to introduce Dr. Keith Miyamoto. He's the global CEO of Miyamoto International. He's a world-leading expert in disaster resiliency engineering, disaster response, and reconstruction. Dr. Miyamoto holds graduate degrees from Tokyo Institute of Technology and California State University. He currently travels around the world to make the world a better, safer place. And if I'm not mistaken, you're not actually in the US right now, Dr. Miyamoto. I think you are actually traveling around the world right now, right?
Yeah, actually, I'm in Marrakesh, Morocco. That's where I am right now. And I made it. Just come from the mountains.
Thank you so much. I'll leave the floor to you.
Thanks so much. So let me share the screen. How's that, Gloria? Can you see well?
Yeah, that looks great.
Okay. Okay. So I think what I want to talk about for the next 20 minutes or so, it's about the focus on the response and the recovery of how the Turkey earthquake went, and what's going on right now, and what could happen in the next this year and next. Just a little bit about company. We're located in about 30 different locations globally, from now Morocco to all the way to Colombia, throughout in the California cities. And as you can see, we're located in a so-called red zone, exposed to hurricane, earthquake, and I guess war now. I spent most of the time in Ukraine recently because of the obvious reasons. So Turkey earthquake, just quick. I know many presenters already talk about this thing, but it's definitely magnitude 7.8, 7.5 back-to-back as large scale, affecting almost 500 kilometers long and 300 kilometers wide. It's a huge area of a country. It's a beautiful area, as you can see, that because of the earthquake always makes this beautiful landscape. And it's pretty close to Elbistan. I went, which is the from Gaziantep maybe to the north for about a couple hours. So it's affecting a lot. I've been around, and I must say this is probably one of the worst disasters I haven't seen for quite a long time. And this is a picture from Hatay, and it's complete destruction. So you can see the 100% buildings gone, essentially. For the impact is affected about 40 million people, killed 50,000, and about 100,000 people injured. And most of all, more than 4 million people are displaced from their homes, and over 10% of GDP for direct damage itself. So on top of an indirect, so it's going to be, it is actually tremendous impact to the Turkish nation here. And if you see that the affected area for about 1.7 million buildings, you can see the kind of this distribution of a so-called red, yellow, green tagged. If there's something we convert to the ATC 20 type of terminology rather than the Turkish approach, about 5 different levels, a little simpler. So looking about the 10% is either red tag or collapsed, and 3% is yellow tag, and the balance is green tag. So this kind of patterns you see quite often many places, but this is a massive scale. After all, it's 40 million people affected by this area, right? So you're talking about this 200,000 buildings is red tag. It's 200,000 buildings. They're not like little houses most of the time. They're talking about 3, 5, 10, 12-story, highly densely populated apartments, essentially. So it's not any means the smaller scale. It's a big scale, and almost 500,000 those mid-rise buildings are either lightly or moderately damaged. Why this happened? Well, Turkish building code changed in 1998. So anything built prior to that, there's no seismic consideration. That's obviously dangerous, you can imagine. But there's something unique about here. What not about here, it's pretty much common, I see everywhere in many countries, has no inspection by the engineers. And that's definitely the killer factor. It's if you see the most of the public buildings like hospitals and schools, and they're usually inspected by the engineers, so their performance is so much better than typical commercial buildings where they skip the actual engineering inspections. So things like that you see quite often. And I saw a lot about the smooth aggregate or smooth rebar. Smooth rebar you find in the older construction, but you see even newer construction, you see the kind of a river pebble, the large scale rocks you find in a system. In older construction, obviously a lot of stories and stuff like that you see. Now, some of the hospitals, I mean, the Turkish building code changed that, the policy changed that. Anything new hospital construction over 100 beds has to have the seismic isolation. In this particular case, there are about 12 hospitals like that in the area, and they are performed very well. Not only they didn't collapse, but they're functional after the major seismic event, just back-to-back 7.8 and 7.4 event, as you can see isolation movement. So assessing damage, this one first case, actually we used the NASA JPL data to see the real-time damage assessment. This particular case is looking at essentially the satellite fly over every 7 to 9 hours, every parts of the world. So you see the difference between the before and after picture you overlay, and that displacement difference you can see for each building stock, so you can tag the building per se. So that's how the figure these things out. And we compare it with our ground assessment. They actually match pretty good, So we use this as a map to kind of guide us to go places we need to go. So this is come from the NASA JPL, the damage map, and you can the granular level. This is Hatay. That's the first picture you saw. It's almost 60% of buildings are damaged, and a lot to do with the soil condition. It's by the river and very soft soil, and older construction, a lot of them, and it causes death essentially. Non-ductile concrete, a lot of them. But even a place like that, this is a newer steel construction and perform very well. Just looking from outside, there seems no much damage at all whatsoever. But soil makes a huge difference, This is a picture, this is a map from a Gaziantep, which is only 3% of building stock damage. It's very close to the epicenter though. It's a lot to do with the this. You see that a lot of exposed rock like that. So it's a bedrock type of formation. So therefore that you don't see much of amplification. So Gaziantep is saved. So it's really come down to where you're at makes a huge difference. If the building sits on the rock, still perform okay, as we see in Gaziantep, only 3% damage ratio. But if the building sits on the soft soil like Hatay, it's complete destruction. So response and recovery. I know there are quite a bit of criticism to the Turkish government about the response of it, but what we saw, we thought that was a very robust type of a response. I was there personally 48 hours, about 2 days after from the earthquake happened. And I saw a lot like this. There's pretty much the urban search and rescue team at every single city or villages. And not only that, the local national ones, but also I saw a lot of international teams. And after something close to like 1,000 members of an urban search and rescue team, international deployed, this is Indian delegates here, and assigned to small villages in outskirts of Epstein. And the equipment's just pretty much everywhere. What happened is the president made a decree that commercial contractors, they need to basically donate the equipment. So they actually deployed all kinds of heavy equipments everywhere. That's something I saw that in about almost 3 days after the earthquake. And I thought this agency kind of equivalent to FEMA, and they provide the several hundred thousands warm tent like that throughout the whole affected area. And this is a picture I took about day 4. It's a very organized format. And you see this kind of organized campsites like that throughout affected area at the time. Now that those tent cities are pretty much gone, replaced with the steel containers, which I'll tell you a little bit more about. Hatay, so Hatay Airport is Hatay is the one that I just showed you, just very, destroyed the city. But this airport shut down for about 4 days or so. So, first, by second week, this is a fully operational and open for the essentially business for mainly for urban search and rescue team or engineers or emergency response personnel. So this is actually very important things. The public buildings perform really well if it's inspected, because as you know, Turkish building code is good as anyone's. So this I was talking about the heavy equipments like that. This, I think, 5th day I took this picture. They are starting doing demolition of the half collapsed or heavily damaged buildings. This by it's a local contractor just deployed their equipments to start taking down. Now, some cases I saw that they're taking down the buildings they probably should not taking down. There is not much of engineering control over that I saw. So, and it was done based on the super rapid assessment, sometimes from just external only. And based on the data, start taking down buildings could be the, throw back the recovery time actually. Damage assessment was very robust. First 3 weeks or so, several 100,000 buildings being assessed for the 5 different categories and have a QR code, each of it. And so it was actually very organized, fast effort. I think the problem is did not cover the communications well. So the residents are always kind of left wondering about what this QR code means and what is the damage, what is the cracks in their buildings or homes. So that was something we're actually working with the government right now for communication campaign. So here's a typical kind of structure or apartment you see out there. It's essentially it's a concrete moment frame construction, but behavior is actually behave as the infill wall. Those infill panels made of either many cases the concrete masonry block units or brick. You see that, and has a pretty thick plaster on each side, so it creates a pretty solid kind of confined masonry type of actions. So in many cases, when they're assigned to be light or moderate damages, they're in fact the cracks in the plaster or cracks in that infill, which is a non-vertical loading carrying walls. So if you think about it, there are over 500,000 light or moderate damaged buildings that essentially look like this. And they should be easy to repair, as you can imagine, back to at least the pre-earthquake conditions. Now, by initial days, the government declared not only the government is going to take down the almost 100 to 200,000 red tag buildings, but additional 500,000 moderate to light damaged buildings. So that made that very difficult conditions because especially the moderate damaged one, you're not allowed to occupy the building, so you're not allowed to repair the buildings even. So you pretty much have to abandon it. And that create the condition where the government provided steel containers in outside of a city. You can see that the sea of this steel containers, so it's a houses essentially, and people live there. It's definitely not a desirable place to live and far from where people work. And it's not very nice. And also the on top of that, government essentially started building the apartments pretty much outside of where the city center was. And plan is to essentially get the people to buy the new apartment to live. The problem of that approach is that obviously the used to be a social center is middle of town, now moved to a completely different place. So the workplace is inside, so you have to commute back and forth. So business have to move to somewhere else. So that makes the essentially in a sense that the social chaos in effect, because it wasn't able to preserve that. So agenda here is the how we can actually fix this 500,000 light to moderate damaged buildings, so people can actually occupy back faster to the place where they live. That's where their city, that was town is, where the village is. So we worked with the U.S. Aid and the Catholic Relief Services and Habitat for Humanity. We're still working through to have a rapid and assessment for really looking into the repairability of it. Looked at essentially first a light damaged one. Now the modern we're looking at what would be a repairability and what kind of methods has to be used, and what is the BOQ, the bill of quantity of each unit. So again, the QR code is attached, and so residents can download, see that what type of repair need to be done for what kind of cracks, and what is the material needed to actually fix it. And same time, we combine it with the communication training campaign, so residents can understand what's going on. So far, our team is a local team, assessed the about 4,000 buildings, which is affecting about 170,000 people. It's an affected area from Gaziantep to all the way to north. Should I show it to you? Osmaniye, that's the toward the west from Gaziantep, and Elbistan in the north of the smaller towns. So we're looking at about 40,000 household. That's the household we're basically looking at, and we have communicated through to each of them. I think one of the probably most important things we're doing that, not only just providing the material information so residents can fix or repair, but that's one thing. But it's actually talking to residences. So this is like a first time essentially they saw the engineers or some just official people show up talking to them. So that damage assessment is just much more than just technical aspect of it. Repair assessment, I mean, much more technical, much more than technical. It's about the communication, about the psychological impact. That is actually such a key part of this so-called damage/repairability assessment we've been doing there. So communication campaign is a very important part of it. We met so far about 7,000 people in the communities and discussed through our findings and how they can use the QR codes and what does the cracking means, and what is the older buildings means, what's the danger or safeness of a certain structural types. So after those discussions, they see that about 85% said they feel better understanding of what they live, and 90% consider they'll come back home if the things are repaired quite right, and almost 100% would share the information with the families and their friends. This is actually, so this communication campaign is, I think this is probably much more important piece of it we're doing it rather than actually repairing things. I mean, repairing is important, but people to really empowered with the information, because after all, no government has the repair that 100% of building stocks or reconstruct. Average is, including California, only 10 to 20% of the damaged assets being repaired by public money. Rest of it, 80-90%, has to be done by private money. So we use a social and mass media, TV and newspapers all over the places to basically talk about this message about the why collapse and why it's collapsed, why didn't someone didn't collapse, and what is the cracking means, what's moderate damage, what's the light damage, and how it can be fixed. And we reached the I think by now for several million people now nationwide, not only affect the area, for both using the social media. Turkey used Facebook a lot, so we used quite a bit of that, and also the TV and news media. Communicate. So, people said that, our activity is translation for the people. At least there was someone calling and asking, it's a minimum requirement, isn't it? We apply to many, we apply to many different places. They're talking about talk to many different places, but they could not find any officials who could explain to us about security or safety or cracking, what does that mean of our buildings. So they are waiting for the excitement for assessments that would carry it out in their buildings. So you can see that how important communication after the disaster. So I think the Turkey definitely got a long way to go, because after all, there buildings will be demoed out and need to be reconstructed, and there's a 500,000 buildings, they are lightly damaged or moderate damaged, so they need to be repaired. And still, many millions of people are homeless today. So it's definitely the even powerful as Turkish nation is, it takes a lot of effort to get up to. And so our job is really to be there with them to kind of go through the whole process to the very end. But that's what we do. That's about it. Thanks so much.
Thank you very much. Very, very interesting. Let's see if, please share with us your questions in the Q&A chat.
Thank you so much, Dr. Miyamoto. I have actually a question. Is there any, possibility we have a good estimate of quantity of like affected housing from the satellite photos?
Question is that if the satellite, the NASA JPL picture assessment pretty accurate?
Correct. Yeah.
I think it's probably good enough. It's definitely measuring with the displacement difference, and so you can see that those buildings move more, does have more damage there. But also same time, it's a capturing the movement. So not only capturing the building movement, but capturing the soil movement too. So sometimes you guys see the big area being damaged, but you don't see that much because all the soil's moving it, ground's moving it, stuff like that. But it's definitely it's a great tool though to really kind of lead us to place where we want to be at, and it does give you the pretty good indication of it. So this is something that we definitely need to use that, which is I think very critical things, to really triage what happened to the city really fast.
Well, yeah, very good. Also, I have a second question. I know you've been traveling in last few months in all over the world, since from Turkey to Morocco to Afghanistan, and I might miss a couple. So, and all of that was like after the huge event. And I want you to just have if you have a comparison between the government recovery or the different types of collapses you saw in different regions. If you have any conclusion and comparison, you can share with us.
Sure. I think usually most of the time government fail. That a lot to do with the right after the big disaster happened, politicians have to make some bold statement. It's true from New Zealand to everywhere. Usually have this grandiose plan of a reconstruction. You see this, just like a Turkish government said about, we're gonna give you free, everything new, right? Which is not possible. I know that. But when the politicians make that statement like that, it really slows things down. I think that's a huge issue, actually. I think it has to be realistic about it, And but those countries or cities, they don't go through earthquakes so often. So they make statement like that. And the exception like places like Japan, right? Japan, they go through earthquake, big earthquake every 5 years. They are reconstructing once every 5 years somewhere. And so they understand the kind of realistic thing. So you don't see that kind of issues there. But we got to be careful about California too, because last earthquake you're talking about in 1994, right? And It's long ago. And many thinks that, well, you know, we went through a big one. Well, it's not really. That's a moderate earthquake. Compared to what happened to the Turkish nation, that is nothing, you know. They went through 7.8, 7.4. You know, ours in the North Ridge was, you know, 6.9 or, you know, something like that, right? 7 maximum. So it's a completely different kind of energy being released to here. So we haven't really seen yet the true earthquake urban disaster quite yet. You know, last one we saw was essentially 1906. But we have this kind of false sense of this kind of safety or ness. I think that's something we just can be really careful. Especially our case is a little bit different issues we have. They don't have an issue about fire after earthquakes because of made of concrete, right? Look at the LA basin, look at the high density metropolitan area we have. Well, good news is made of wood, so chance of collapse is fairly rare, right? But bad news is those things get burned, you know. So, you know, Dr. Charles Colton, you know, he did some certain research on the subject matters, and expectation is the you know, simultaneous ignition of over 1,000 houses burning one after the earthquake in LA basin. No wind. Just think about that, you know. So that's something that when you got to think about. But see, that can be prevented or reduced quite a bit by the automatic gas stopper, you know, the natural gas stopper thing,
right?
Which is it's a good thing we put for new houses maybe, but not for old stock of houses. You know, it's we're definitely looking at some major fire disaster there. That's what's going to happen. Just like we saw in 1906. I don't think we changed that much, that part of it. Building code changed a lot, but not this fire safety aspect of that.
Great point. Thank you so much.
And we have a follow-up question actually regarding this. Nicola is asking, you mentioned the importance of repairing light to moderate damaged buildings. Did you consider retrofitting such buildings according to the latest code provisions? If yes, which retrofitting methods do you believe are most suitable for the Turkish context?
Shear walls. I think that it's a shear walls like a no-brainer, right? I mean, that it just can go wrong, you know. And it's I think the problem with the Turkish construction is even new one too. We don't know what's in there to actually, and most of the time you're going to see the you don't have good materials, you don't have good steels. They have enough materials, but doesn't doing it right for, like, you know, little 135 degree hooks or spacings, little things like that, hooks. So it's obviously semi-ductile or non-ductile concrete structures. So, you know, I think that adding just concrete shear walls just take the 100% loading. I think that's a very, you know, kind of simple way to doing things, but it works, you know. And I think that would be, to me, like right way to doing it, especially at the place where a lot of the soft soil exists. Just change the frequency content to a little bit higher frequency, right? I think that is really key there. So, you know, I mean, when we look at seismic retrofit, we don't really carefully look at the systems versus the frequency content, you know. But to me, frequency content of what's going on is like a probably most important aspect of it, you know. So most of the time, I think concrete shear walls in the soft soil should works really well, you know. I mean, obviously, you know me, you know, I like viscous dampers and stuff like that, right? But if you don't have a good backup system, if you don't know what's in there, it's kind of hard to just put the viscous dampers, you know.
Exactly. We have one more question for Professor Comfort. If she's Dr. Comfort, could you please expand on your statement about the changes adopted after the 1999 earthquake that we are not sustained?
Yes, this was actually one of the critical issues that was raised, and an issue that was very, very controversial in the city. And it was also an issue that EERI members, Polat Gulkan and our colleague in Velocity University also said, because they had worked on the earthquake codes, they said largely in the cities, the professional engineers had, really been trained to follow the codes. But the point that Kit made, that there was no inspection, is the critical point. And then in the smaller cities, and these were smaller cities, Antakya, Gaziantep, Gulbasi, the earthquake engineers in those smaller cities were not that well trained. And then there was no inspection. And then lots of rumor, and here I'm just reporting what we heard, a lot of concern about contracts that were given to party members for construction that really was not up to code. And local administrators who signed off on the contracts, largely because they were not familiar with the code. And so this is a critical problem in raising the level of professional understanding of what the codes are, training the engineers. And this was the point was made again and again. There are 120,000 structural engineers in Turkey. There is no shortage of engineers or engineering knowledge, but it's getting that knowledge to the right places and then getting, and this is what I'm very much interested in, the organizational structure in place so that you do have inspections and you do have a sufficiently strong local political council that can hold the mayors and the contractors to account in issues like this. And so that was a very large part of the discontent, and unhappy response on the part of the people who lived in these buildings. And they, of course, had invested, many of them, their life savings in buildings built, 3, 5, 7 years ago that collapsed or were heavily damaged.
That's horrible, actually. And I agree with you, Dr. Comfort. I mean, it's true that if you go to Istanbul, or Ankara, yes, you're going to see the probably world best engineers in the cities.
Right.
But if you go to little small towns, no, you don't see anything, right? And exactly. On top of that, there's no license system there. So if you got a Bachelor of Science in Engineering or something.
Well, these small towns all have universities. There is a university in Gaziantep.
An engineer, contractor too.
And it's really getting the knowledge to the places where they need to use it most. And this was, we were talking with the professor of public administration at Ankara, and he had trained most of the emergency managers, the people who were the administrative officials, the local officials in these communities. Regrettably, they had all been changed. And this was a political change where, as administrators in the towns, in the cities and towns, they insisted that their engineers doing the contracts follow the codes. And they were removed from their posts with people who were replaced, who were loyal to the governing party, but did not have the training. And so this was also, I'm sorry to say, a major issue in the country.
Yeah, but at the same time, though, I mean that if you see what happened in the public infrastructure, like bridges, like a whole bunch of bridges everywhere, right? But those systems are, highways everywhere in the affected area. I mean, they are literally open at the simultaneously. There's no damage at all whatsoever.
Well, those were, but those were
done by PPP. Okay, that was done by the
exactly. Those were done by national engineers.
Engineers.
Yeah, national engineers who knew what they were doing. Turkish engineers. Who knew
it's all done by different contractors.
And so this is the point. The knowledge and the skill is in the country.
That's right. Exactly, that is correct.
Getting to where it's needed and used is the
I mean, Turkish building code is as good as anywhere. And
Exactly.
you know, and they're probably one of the most advanced one. I mean, they probably have more base isolated buildings than we do. Okay,
Right.
in California. And I mean, it's a very advanced country, just no question. But like our engine company in Istanbul, Miyamoto Istanbul, they don't take any commercial projects anymore for a long time because they don't pay to do inspections, you
Right.
know, so they don't want to take liability. It's quite a long time now. You know, they have not done any commercial buildings for quite a long time. So it's a shame. It's definitely but I do believe though that's going to change. And because the cause is crystal clear, you know, it's kind of too bad initially they make a big deal out of corruptions and put people in jails and stuff like that. I'm sure some people cheated, okay? No question about it. I'm just saying that everybody in Turkey is angel, okay? There's some people evil, for sure, just like here. But it's not about corruption. It's about whole system of
Right.
no licenses, no inspections. I mean, those are bad on top of the soft soil.
Right.
It just collapsed. So you killed 50,000 people.
Yeah.
But at the same time, though, collapse ratio is around 2% of whole affected area. You know, expectations California, we will see 1%. You know, especially we do have a lot of older stock buildings too, just like they do here. Okay, so it's not like we're immune from what they experience out there. It's just it's a huge area, it's a high density area, 40 million people. You know,
Right.
so we're
What's-
going to see the proportionally, bad things happen to our country too in California.
But what strikes me, Kit, is this is not as much an engineering problem as it is a social
That's right.
organizational problem.
That's right.
And we really need to pay attention to that, not only in Turkey, also in California, and also in other countries around the world. I mean, look at Morocco and the earthquake there. I mean, a moderate earthquake under the best of circumstances, there shouldn't have been that level of damage, that level of death. But
Well, yeah.
it's really, really a major issue getting the organizations and the people to understand.
Yeah, I mean, Morocco's case is a little bit different. It's affected area, mainly the vernacular architecture made of rocks and clays. And but
true.
at the same time, that if they build the vernacular architecture right,
Right.
actually perform really well. You know,
Yeah.
you know what I mean. Use slate rocks and connected to it in a thick wall. I mean, just perform really well. But problem is that people start cutting corners out of some big round rocks and stuff like that. Then so of course doesn't work. But yeah, it's a little different context. But yes, it's definitely it's there. But to me, as I said, I think California really issues of fire after earthquake. I mean, that's something we don't really talk about much at all. But it's a huge problem. You know, we will lose whole LA basin. You know, and I mean, think about 1,000 fire ignition at the simultaneously. Can LA Fire Department can help? No, of course not. Just think about that. I think that's something that we should really start seriously talking about it. You know, it's actually that you can change $20 just gas meter thing, make changes. You can actually automatic shut off of the natural gas. You know, like they do in Japan. You know, so there's no. We don't talk about it, so that's what no one knows about how risky this thing is.
And you know very well, Kit, that was the difficulty in the Hanshin earthquake in 1995.
That's right. Yeah, I mean, 6,000 people burned to death, and that changed the policy, right?
Yeah.
So we don't have to wait for someone to happen to us. In a sense, we have so much things we can learn from a global scale to make changes.
Yeah.
Exactly.
Yeah,
it's very expensive to see that. Yeah, as you mentioned, both confirmed that the engineering knowledge is pretty great in those countries in Turkey, but quality control, construction quality management, risk management, everything probably caused the issue. Thank you so much.
I was just going to say, and then that cascades into other impacts on the community, public health, education, business development, and the whole community suffers and it becomes much more difficult to rebuild.
Yeah.
Very important. Yeah. Well, I like this nicely lively controversial discussion. We should have more of this.
Yeah, this is perfect. We have actually one more.
Yeah, there you go. Come to me.
I have one more question actually to follow up on that.
Sure,
If
go ahead.
that's okay.
Alvaro.
If there's time. And for some reason my video doesn't work. But the question is basically related to the inspection. We know that in the US we have inspection that is enforced by the code. We have structural observation of the design engineer.
Yeah.
And if I remember correctly, but maybe correct me if I'm wrong, in the Turkish newer code, this is also required, at least the inspection. But correct me if I'm wrong. You did mention that the public buildings, and this is something we also observed, were fared better, right?
Yeah.
Is
Yeah.
there inspection happening for those buildings or not? And also, in your view, you two have traveled to many countries, and the inspection issue is always an issue. Is this getting better around the world or not?
No, not really. It's getting worse, as far as I can see it. But you're definitely correct. Those public buildings, schools, and hospitals, they are inspected by the design engineers as a requirement. You know, that's why
Right.
our office do that. You know, we take buildings because we can ensure that. I think contractors, I don't think they try to cheat anything. I think they don't know why they're doing this thing. They cut corners almost. I don't think they're saving much money. They just cut little corners because they don't know why. I think that's why the inspection is important, isn't it? You know, when I go to the construction site, in many cases, you talk to the contractors, right? The labor said you got put 135 degree hook. The kind of discussion with the contractors and laborers. You know, I think that's a very important one, actually.
But I would say that in some of the instances, and actually with many of the people that we did speak with in Turkey, in instances where inspections had in fact been done, they'd been done very cursorily. So someone had come out one day to inspect a very large building and essentially just signed off on it.
Mm-hmm.
And so again, it's who does the inspections, how carefully are they done, and what happens when they are not done. One of the things that Erdogan had done before the 2018 elections is Turkish engineers themselves, the professional engineers, had gone to a number of cities and looked at the buildings and said, these buildings are not safe. These buildings will have damage. And yet the buildings were built and people were living in them. And Erdogan had issued an amnesty to the contractors who had built the buildings and said, oops, sorry, we made some mistakes, but the buildings are built, so we're just going to not hold the contractors accountable. This was a major issue, highly politicized issue in Turkey at the time, where the government, the national government, excused the contractors for not following the codes.
Right.
When that happens, what does the next contractor do? Oh, I'm supposed to follow the code. It's going to cost me more money to follow the code. I'm not going to follow the code. And that set a really damaging example for other contractors and buildings in Turkey.
I would offer that the contractors need to follow the code, but they would do it if they are paid for it, right? In the US, the owner pays for the inspection and the contractor enacts that inspection. So I would say it's more the owners that need to pay for that. For example, the government pays apparently for inspection in their public buildings, right? So it's a complicated issue, of course.
Well, the issue that you made that is true, I think it's written in the code, but following the code is a critical issue.
Right. Thank you.
I think one of our participants, Mona Hijazi, she's joining from Iran, and she's confirming that this is the same problem in Iran, that there are problems and this issues after earthquake is instead of being engineering issue, is mostly the social issue, people trying to make things cheap, and quality control and risk management stuff. So it's all over the Middle East, at least we can say.
You know, one thing we done quite a bit in the past, and especially like a place like Haiti, you know, where there's no way to do any kind of inspection, right? We actually did a mass campaign to the homeowners, like how does this ACI 318 detail look like, and why I need to do it? You know, well, I didn't say ACI 318, but you know what I'm saying? You know, so very simple key messages like that. So essentially that those home owners or residences or renters, they see what's a good construction look like, you know? So to me, like they're like a last line of defense, right? In Haiti's case, a last line of defense. So we train like tens of thousands of people like that in the past. So it needs to be like become a social norm, I think. You know, I think that's very, very important.
Yes, that's actually very insightful. I was about to ask you this, what if we kind of turn the power to the people, to the community? So, I mean, this is basically what you said right now. If we are able to inform them enough, but not too much, because of course they cannot become engineers, but we are not doctors, but we know if something is not right with our health, maybe we could do something similar for the buildings.
Yeah, that's so true. That is so true.
I quite agree. And I think this is where the real pressure needs to come from. And it's especially important in Turkey because building construction has honestly been a form of wealth creation. And people didn't trust any kind of investments, and Wall Street investments in Turkey were not particularly strong. So people looking to protect a retirement would buy another building. And if they know that their life savings are going to be lost because there's no adequate building inspection, that would become a very important factor. And this is literally basic education on building construction for people. And this is why, I'm a social scientist, but I would advocate that every entering university student take a basic course in engineering to understand how buildings are put together and why it's essential to have a design, a code, and inspection.
For sure. As you, Louise, and Keith both mentioned about the infrastructure and bridges, actually our next speaker is he was part of the EERI reconnaissance team, and his presentation focused on bridge and electrical infrastructure reconnaissance in Turkey after 2023 earthquake. So we're gonna move to Dr. Ezra Jambuli. He's a senior managing engineer at Exponent, who specializes in evaluating the performance of structures subjected to extreme loads, such as earthquake, wind, and flood. So Ezra here, please.
Thanks very much, Hamid. This presentation has a slightly different flavor than the other two in that it's more focused on damage mechanisms, but transportation, not just bridges, transportation and electrical infrastructure are quite important for assisting both emergency services after disasters and then the ensuing recovery that occurs. So I'll touch a bit on that. So as Hamid mentioned, I was part of a team from EERI. EERI sent 3 teams in the field, and this was a team focused on Lifelines infrastructure. So more than just bridges and other transportation, electrical infrastructure, but also looking at water infrastructure, wastewater treatment facilities, energy and power, basically anything that is necessary for the functioning of society, really focused on more distributed systems. We had a fairly large team with 8 engineers from the US and 8 engineers from Turkey. Additionally, the team had diverse expertise, which is really necessary when you're looking at lifelines, because each individual type of lifeline infrastructure is quite unique. There's a big difference between a bridge and a wastewater treatment facility, for example. There also was a wide range of post-earthquake reconnaissance experience. So that was quite useful for drawing comparisons for where we've seen in other countries after other earthquakes. And in addition to acknowledging other members of the EERI team, I think it's important to acknowledge numerous colleagues and just people off the street in Turkey who were quite helpful and quite resilient. I don't think many of these observations would have been possible, and certainly not as informative without the context of people who were in the field, who lived through it and are still living through the disaster. So thank you to them. I think it's important to understand the earthquake sequence a bit and how intense this earthquake was to make any sort of judgment call on whether the performance of transportation and electrical infrastructure was good or bad. Was it expected? Was it not expected? So this was a series of very intense earthquakes. The first event was a magnitude 7.8 in the middle of the night, and the same day, magnitude 7.7 in a different location. And it wasn't just those 2 large earthquakes on the first day. There were a number of aftershocks greater than magnitude 6, including in particular a magnitude 6.3 on February 20th, 2 weeks after the initial earthquake in Hatay near Antakya, that because it was so much closer to that city than the substantial, there was like 11,000 aftershocks and many greater than magnitude 4. So very intense earthquake sequence just based on magnitude. And in terms of intensity measures that we typically use to think about what the responses of structures, the peak ground accelerations were quite high, greater than or up to 1.2 Gs, that varied over the region as a function of directivity effects, near fault effects, and basin effects. And in Antakya in particular, there were incredibly high PGA values that were recorded. And if we can see that just looking at a contour map from USGS, showing how intense the earthquake was in different locations. This is a very large region. The fault ruptures were hundreds of kilometers long. So when we see areas this large that had 0.5 Gs of peak ground acceleration, this is really an enormous region that was experiencing incredibly intense shaking. And the fault ruptures were quite large as well. There were high vertical components of the ground motion as well, in some cases exceeding what the design spectrum and what we in the US call the maximum considered earthquake spectrum were. Just overall a very intense earthquake. And then maybe the best analogy I have for how intense the earthquake was is thinking about it in terms of peak ground velocity, PGVs, that tend to correlate very well to what damage you actually see in structures. And before the 1995 Kobe earthquake, I don't think many people thought we could get PGVs greater than 100 centimeters per second. I think some folks thought it was theoretically possible near fault. Kobe taught us that you could get PGVs greater than 100. They weren't that much greater. We saw PGVs going a little bit greater than 100 on some events since then, but this earthquake has really shattered those records with PGVs exceeding 200 centimeters per second, which is just an incredibly intense earthquake. And it's a function of having many recording stations and having many populated areas built right along the faults, which is probably not wise in hindsight, though I don't think it's hindsight now, because historically there have been a lot of very intense earthquakes in this part of the world, something that should be expected. I'll get into discussion of the transportation systems, how they performed. And I omitted slides on airports, so I'm glad to see that the kit actually included some particular on the Hatay airport. So I'm going to focus on the performance of bridges and viaducts, so bridges that don't go over rivers, tunnels, and roadways. So the EERI team visited a large number of bridge and viaduct sites. It was 66 sites, some of which had more than one bridge there. In certain cases, different bridges that were built in different eras at the same location. It's quite interesting to see. The location of the bridges are shown by black dots in the map on the right-hand side. So one thing you'll see is that a lot of the bridges we observed are very close to the fault. We did nearly full population survey of river bridges in Antakya, saw every bridge along one river in Iskenderun as well, and then worked our way up the fault, observing a lot of bridges near some of the larger cities and towns, as well as seeing some bridges in particular in Elbistan, which is fairly close to the first magnitude 7.7 aftershock. Overall, we saw 2 collapsed bridges, 8 that we would categorize as having severe damage, 13 with moderate damage, and then 75 with what we categorize as little or no damage. And I want to emphasize that doing reconnaissance, it's important to see not only damage, but also undamaged structures to get a sense of what's working, what's not working, and then it's useful for developing relationships between the type of construction and the expected damage given some intensity of earthquake shaking. And you can't do that if you only go to the most damaged structures. So I'm going to discuss some common issues we saw, and then as I go through some examples of particular bridge sites, we will encounter all of these. One of the main issues that we saw at bridges that were more heavily damaged was that there was incomplete load pass from the bridge deck to the supports at ends of girders. And the reason for this was typically twofold. Sometimes these occurred in the same locations, sometimes only one of these conditions occurred. One was that there are typically not end diaphragms between girders at supports at many of the damaged bridges. This is something that is uncommon in places like the US, where you would always have end diaphragms between girders near the supports and also along the girder. Without those end diaphragms, girders can move independently from each other. There also were undersized or insufficient number of shear keys between girders at the supports, really just not a lot of restraint in the transverse direction of the bridge. So the restraint that was there tend to be beat to hell. There was longitudinal movement of the bridges that stemmed, one, just from the earthquake shaking, and two, from some of the soil behind abutments getting pushed out of the way, and then the bridges moving. And they tended to be more susceptible to movement when they had thicker elastomeric bearing pads. Those tend to walk out relative to short pads that really can't deform that much. And there were a lot of instances of abutment settling, and then along some of the rivers, particularly in Antakya, embankment failures and lateral spreading at abutments. Finally, in some locations, we would see leaning and residual drift of bridge piers and abutments, and this occurred both in the longitudinal and the transverse directions, and could be a function of both either the shaking or of some geotechnical issue that occurred at the site. I'll go through a couple of examples now where we'll see some of these. And the first one is the Bakir-Karabachak Bridge, which is in Antakya. And this was a pretty critical bridge. In the upper right, we see a photo of a debris site. So there were many, many collapsed buildings in Antakya, and you have to bring the debris somewhere. So this site up in the hills was designated as that location. And there really were not very many bridges that could support truck traffic to bring debris from the city to that debris site. And this was one of the bridges that was being used for that, for better or for worse. There were not a lot of bridges that could support heavy traffic near it. And this bridge underwent extremely intense shaking. The peak ground accelerations were 0.6 Gs and very high PGVs as well after the first earthquake. And then it was hit again in the aftershock on February 20th, 2 weeks after the first two large earthquakes. So this bridge underwent two significant shaking events, but was still being used. Now, how was it being used? There were two bridges at the location, and both of them had settlement on the ends of the bridge around the abutments relative to the main bridge deck. And one of those bridges was just left that way. It's almost a foot gap here. Probably not driving over that. On the other side, soil had been placed so that people could actually drive over this bridge. And I thought it was pretty amazing to see that this occurred. And it's one of the few bridges that I've actually seen loaded with the full AASHTO loading of something like 15 trucks on the bridge all at one time, all filled with debris. So that was quite amazing to see. But a bit nerve-wracking to cross because there was significant damage around the bridge. So in the upper left, we can see some embankment failures next to the bridge, and this allowed for some of the soil behind the abutments to be pushed out of the way more easily, and then that bridge can move more in the longitudinal direction. And sure enough, we see that. This is looking at the bridge that was not in operation, that didn't have that soil put it at the edge of the roadway so that you could drive over it, and it was leaning something like 5 degrees from plumb. We measured this with the plumb bob while we were in the field. On the other side of the bridge as well, we similarly see failures of embankments, which is quite dangerous for this bridge. Another example of a bridge in the Antakya area was near the Hatay Stadium. And this was a pair of bridges that were quite important because they served a hospital. But unfortunately, they were immediately adjacent to the fault. At the time that the EERI team visited the site, the bridge was closed and there was a worker there, I think taking some soil samples, and he said that the bridge was going to be demolished very, very soon. This bridge also was subjected to very intense shaking in the first earthquake, the magnitude 7.8, and the February 20th magnitude 6.3 earthquake. Very high shaking intensity in terms of PGA and PGD. And this bridge is an example that experiences a lot of the classic damage patterns that occurred in this particular earthquake. You can see the stadium in the background here. So one thing you might notice is these shear keys on the outside of the bridge. These are quite cracked. This would be from transverse movement of the bridge. And these are not very thick elements. So one would hope that there would be some shear keys between some of the intermediate girders as well. But that was not particularly common, certainly not between every girder. This bridge also saw some settlement around the abutments. So this roadway normally would have been flat, but was not the case because of that settlement, and asphalt had been poured. So even though this bridge was closed at the time, the EERI team observed it. At some point, someone had probably been using this, or this new asphalt wouldn't have been there. On the other side of the bridge is a bit hairier, and I wouldn't think it'd be too wise to drive over that, independent of what was going on structurally in the bridge. Something we saw at this bridge that we also saw at some others was that the ends of the girders, the webs, saw significant spalling. The rebar was very exposed, and we can see this shear key also deformed and almost falling off the end of the bridge from transverse movement to the bridge. So one of the reasons this is happening is that there were not diaphragms. One of the common things we saw, you don't see any diaphragms between the girders here. So the bottom of the girders move independently. On the top, maybe they move together because they're all attached to the deck, but overall, these girders are not going to move much together. So because they're moving independently, they can rock, they can rotate a bit, they're not really restrained at the bottom that much, you start to see damage to these webs. And then there aren't really much shear keys resisting movement. You can't really see some of them here. It's partially because they were missing from certain locations, and partially because the ones that were there got beat to hell from the transverse movement of the bridge. Another thing that was quite common was that the bearing pads were deformed. So in this case, this bearing pad, it normally would have been supported by the pier cap, but it has come out, and there's only maybe half of it or less that's still supported. And so these are really walking out during the longitudinal movement of the bridge. There's something going on between that friction interface relative to the stiffness of that bearing, so the bearings can walk out. I don't think they're keyed in. And some of them, they don't just start to move out, they move all the way out. On the right-hand side, we see a whole bunch of these bearing pads that popped out during the earthquake. And then some classic damage that you see, which is kind of what you want a bridge to do, is you want to see hinging in the piers when there's a very intense earthquake. So we saw that in every pier in this bridge, plastic hinge zones forming, and we see all the spalled concrete and exposed rebar here. Another example of a bridge is getting away from the city areas and moving more into agricultural bridges. And so this bridge in particular was quite important, but to a relatively few number of people. Served a small village in an agricultural area, but it was the only bridge crossing this river, something like a 30-40 minute drive. The bridge was technically open to traffic at the time that the EERI team visited, though we chose not to drive over it for reasons that will probably be obvious in the next couple of slides. And this bridge in particular was subjected to intense shaking during the first earthquake, but not during the subsequent ones. So this bridge had significant lean after the earthquake. And one of the reasons for this was that there was a major soil failure near it. Here we see lateral spreading on one side of the river. And looking at the abutments, you can kind of tell in this photo that this one is leaning quite a bit, and that's stemming from the soil movement. One other thing that you may notice on that slide, but is a little easier to see here, is that there was permanent deformation of this pier, leaning quite a bit. And the girders, normally you would see this gap between the girders at the center of the pier. That's probably where it started, but they moved quite a bit during the earthquake. And so this fortunately didn't come off the end of the pier cap, but came pretty close to. So not only was there residual deformation in the longitudinal direction, but we also see some residual drift in the transverse direction of the bridge. You can see this pier is leaning over towards the right-hand side. And one thing that plays into the next topic of conversation, which is going to be the electrical infrastructure, is the bridges carry more than just vehicles and people over them. They also tend to carry other types of lifeline infrastructure. And this bridge in particular carried a whole bunch of electrical cables. There was a major substation just to the right out of view here, major substation in Antakya. So if you lose a bridge, you're maybe losing more than just that bridge. Taking out these cables would be hugely problematic until someone could relay them. So beyond bridges, the EERI team visited some tunnels. There were not a lot of tunnels and not a lot of reports of damage to tunnels at the time of our site visit, but we did hear that there were a few that were damaged. So this one is the Erkenek tunnel, and it was subjected to fairly intense, but not as intense as the bridges in Antakya, shaking with PGVs 50 and 67 centimeters per second in two of the earthquakes. So the lining in this tunnel was pretty heavily damaged. We see some major cracks in it, and amazingly, the bridge was open, and we had heard reports that of the two bores in this tunnel, one of them was open and one of them was closed. And when the EERI team got there, I think both were open, but we're not aware of any repairs that had been made to them. So I guess some debris was cleaned up and a decision was made that perhaps these were just too important. It's a major highway that runs through these tunnels and no easy way to get around that. So if the tunnel is not immediately collapsing, perhaps it can be used. Roadways, we observed a lot of roadways, obviously, because you have to drive a lot to go from site to site. And the roadways themselves generally performed well, but were subjected to two main types of damage. One, stemming from geotechnical issues. For example, when there was surface fault rupture through the roadways, embankment failures, or lateral spreading. And also when roadways were blocked due to heavy building damage in some of the urban areas. So on the left-hand side, for example, this is in Antakya, we can see that there was an embankment failure and this ripped apart the road. So you could actually still drive on this because there were multiple lanes originally, and so there was a little sliver that you probably could drive on if you needed to, though not necessarily recommended. And then on the right-hand side, this is down the street from the photo on the left. The original road did not go where this car is driving on the left-hand side of the photo. It originally went through this path on the right-hand side that has some metal siding put up. The reason that metal siding up is there was a building there that collapsed and debris was in the road. And you obviously can't drive through that, and it can take quite a while to clear debris, especially when things like roads and bridges are blocked. So this appeared to be a makeshift road around that debris. So some other examples of roadway damage is when there were rock slides and landslides blocking roads, and then when there was surface fault rupture as well. In this case, on the right-hand side, the road was offset by about 10 feet. Easiest way to tell that is by looking at the lines. Here's the dashed line going down the middle of the road, and then here's the dashed line on the other side of the fault. I'm going to move on and talk about electrical transmission, distribution, and substations. Now, another critical part of recovery and emergency operations. So a little bit of background on the electrical system in Turkey. Much of Turkey has underground lines, but the older areas tend to have overhead lines. And the region of the country that was affected and hit by the earthquakes is a relatively older area. So because of that, there were a lot of overhead lines in this area. There was reported substantial disruption to electrical power service immediately after the earthquake that was restored gradually in various areas with various success. So in Antakya, for example, there were about 2,000 workers and 500 cars deployed right after the earthquake, and they replaced about half of the distribution system there. Generally, when the EERI team was there, we had access to power, and we had heard that the distribution system was largely up and running in a lot of areas we visited, but there were still issues on the transmission system. And one thing that I think is quite a success is there weren't reports of conductors starting fires. And in the US, you hear about conductors starting fires all the time. If they slap into each other, if they fall, they get hit by a tree, if some debris gets picked up and it bridges between the phases. So it's quite remarkable there were no conductors that started fires after these earthquakes. So an interesting example of damage to electrical infrastructure we saw was to a steel transmission tower. This one was hit by a landslide that had blocked the road, but that had been cleaned up. This tower was supported by 4 legs and 4 piers, and 2 of those piers were in soil that was taken by the landslide. We can see one of them on the left-hand photo, but 2 of the piers were not taken by the landslide. They were in sort of the upward section above where the soil started to move. So this essentially ripped the base of the tower apart. You start to see buckled members, and the tower collapses. What's interesting about this example is in the photo on the right, we see in the background a tower that is still standing. And this was a completely undamaged tower, no equipment damage either on this tower. And I think it goes to show that for light structures like this, yes, it's quite tall. It experienced the same intensity of shaking as this structure. The one that was subjected to the intense geotechnical condition, in this case, landslide, performed very poorly and collapsed, whereas the one that was only subjected to inertial forces was okay. And this, I think, is a common theme in the performance of electrical infrastructure. So another example is a rock fall. This massive rock here that's probably 3 times my height started on the top of this hill and rolled all the way down. And you may see a wood pole here. This was not the original structure. There were concrete distribution poles here originally. The wood pole is the replacement. And there's a whole bunch of wood poles here, all of which had to be replaced after the earthquake. And as you can imagine, with a rock fall like this that continues all along the road, it didn't just take out the distribution poles, it also took out the roadway. So the distribution company was not able to repair it by sending a car in. They sent in a helicopter with replacement poles so they could get the distribution system up and running. And here's what that one of those concrete poles that hadn't been removed yet looked like when it's hit by a rock fall, which is not particularly surprising. Another common issue in the performance of distribution structures was the way that a lot of these concrete poles were anchored. So this, for example, you can see the concrete around the anchor for this pole is all busted up, and the pole is leaning quite a bit. They tend to use relatively shallow foundations that in many cases don't appear to be reinforced and are not embedded very far into the ground either. And that is going to be susceptible to, if anything pulls on the conductor, you might pull the pole down before breaking the connection from the conductor to the pole. And so one interesting example, we see the before photo from Google Earth on the left-hand side, and this fell, it was right over a bridge actually, and the pole managed to clear the bridge, and the foundation completely intact, sitting below, really was not embedded very far in the soil, made it susceptible to earthquake shaking. And the issues with pole anchorage play out repeatedly in some of the cities. So here we see an example of several in a row leaning, being pulled on by conductors. And then we can see examples of poles out in the fields as well, leaning quite a bit because of anchorage issues. In addition to problems with the structures themselves, electrical infrastructure in a dense urban environment naturally is going to struggle when that dense urban environment has performance issues. So in Antakya, there are many examples of buildings collapsing or partially collapsing and hitting the electrical infrastructure. Here we see a building that collapsed on a distribution pole that is in the rubble. And here's another example where a structure has collapsed and it has hit a steel lattice structure that was part of the distribution system and was bent quite significantly. The poles did have some interesting issues. Here is one that appeared to have some interesting spalling in it, and the rebar was quite corroded as well. The reinforcement is pretty small in here, though. So one thought we have on this is that because the reinforcement is small, when it's corroding, it's probably not corroding enough to actually spall the concrete. So something that would be difficult to observe and then repair. Equipment was also damaged. There's a lot of equipment that was mounted on top of structures that could fall over and then disconnect. We see that on this lattice structure on the left-hand side. And on the right-hand side, we see some of the AFAD tents. This was in Elbistan, and so this was set up by the FEMA equivalent, AFAD. And this mobile substation here has fallen over and it's roped off. And I'm actually not quite sure if this was here before the first earthquake. It would surprise me. It looks like it's potentially providing some power on a temporary basis, because you usually won't see substations like this out in the field other than after disasters. Potentially it fell over during one of the many aftershocks that occurred. Turkey also has a lot of substation buildings. So you often will see substations out in the fields. That's both in the US and in Turkey. And Turkey places a lot in urban areas as well. And they're typically 2-story high structures that are concrete frame with masonry infill, but there is not some sort of thick slab at the second level. So these are spanning quite a bit with just some relatively small ring beams at second level. You don't get much diaphragm action there. And these buildings are susceptible to a variety of damage states, ranging from the infill falling on equipment and damaging that equipment, falling outside the building, hurting people, and then the buildings collapsing as well. And just like other electrical infrastructure, when these substation buildings are in denser urban areas, they are vulnerable to other structures collapsing. So on the left-hand side, you see one of the substation buildings that was next to a minaret, and that minaret collapsed directly on top of that substation building and collapsed the substation building. And substations out in more rural areas are also subjected to rock falls. This was an interesting case where the rocks came down the hill and it struck the corner of the building, but quite luckily the equipment was on the other side of the building. So the equipment was not damaged by this rock fall. So to summarize, the transportation infrastructure, it's an important component in outage duration and service efforts. Very important to have roads and bridges that are functional after earthquakes. There were significant bridge disruptions in heavily populated areas, but people seem to be using the bridges anyway. Those bridges are often used to carry utilities, so their poor performance can have significant impacts. Overall, though, I would say that given how intense the earthquake was, to see relatively few bridge collapses and see the bridges at least still functional, even when heavily damaged, that is an encouraging sign. The electrical infrastructure also had interesting performance. The overhead structures generally performed well, but there were a number of conditions that made them more vulnerable. So one, when there were geotechnical conditions like landslides or rock falls, then overhead structures were damaged. Also, things that are difficult for electrical companies to deal with on their own is adjacent failures. You have to build your infrastructure in a city if you want to service that city. So when those buildings collapse on your structures, there's not that much you could do about it when you're using overhead structures. They also had issues with insufficient pole anchorage. The substation buildings, interestingly as well, were also affected by adjacent structural failures, but because they are buildings and some of the issues with building construction that Kit in particular highlighted previously, those buildings often did not perform very well, and the equipment could be damaged even if the buildings were okay. So as a teaser to some continuing work, the EERI team has combined our many bridge observations with Turkish team and some other people who did reconnaissance, who looked at largely different sets of bridges. So we have a database that hopefully be public at some point and do things like developing fragility curves for different damage states for specific types of bridges based on age, different measures of intensity, which hopefully be quite useful for performing risk studies and really understanding vulnerability of similar types of construction. With that, I want to thank everyone for their time and EERI San Diego for inviting me to speak. I'm happy to take questions.
Thank you so much, Ezra, for the wonderful presentation. It was very comprehensive. Before going back to the questions that everyone has, just very quick, have you been exposed and being able to visit any power plants, if there was in that area?
Yeah, so the EERI Lifelines team did visit a few power plants as well as some hydroelectric facilities. I didn't talk about them here. There's only so many things that you can discuss, but there were issues with equipment being damaged. I think a lot of the facilities did not have black start capabilities, and so they needed to be reconnected to the grid to begin generating power again.
Okay. That's good. Andrea is asking, some people say that Turkish people started retrofitting their buildings, but they count on the fact that there will be no strong earthquake anytime soon. So they are not doing the retrofit reasonably. Is that true? Any of our speakers can jump in about it.
Yeah, I think this is also related to what Louise presented, right?
Very much related to it. And this is the whole critical issue of communication. There were lots of rumors that were circulated. Many of them were inaccurate. And this is maybe one of the most troubling one. That we've already had our earthquake. There won't be another one for 800 years. So go ahead and retrofit your buildings. And this really is where, informed local people, good journalism, scientific panels like this are very important. I know the Middle East Technical University group did go to some of the smaller cities and make presentations, and I think that's a very important strategy.
Great point. Ezra, we have two questions from Uzgur. Uzgur is asking, I'll go one by one, actually, two good questions. And question number one is, what is the contribution of vertical ground motion component on the observed damage in bridges?
Yeah, I'm not sure. Based on a lot of the damage that we saw, that could be driven primarily by the horizontal components of the ground motion.
Okay.
Yeah, I don't think we saw any signs of vertical modes forming in bridges. And generally, the frequency content is much higher than the horizontal components, and it's
right.
the horizontal component that's primarily impacting the performance of bridges.
Right. His second question is shear keys he believes are fused type elements, sacrificial components. So if the shear keys are oversized or more shear keys are constructed, that will increase seismic demand on, I'm just reading his point, seismic demand on the substructure component, as well as increase seismic demand on superstructure beams. What do you think about that?
Well, they certainly performed like fuses in that they were heavily damaged, but you need some restraint in the transverse direction. And it's really the combination of not having large shear keys and then not having end diaphragms that allow the girders to move together that was really problematic here. Yeah, maybe the bridge starts to slide a little bit, and that might be helpful on substructural elements, but you know, we generally design bridges so that those piers will hinge, right? That's the target performance in them. You don't want the girders moving independent of each other. You can have a girder collapse. You don't want the shear keys failing either. The point that the bridge move or the girders move off the pier caps. That would be really problematic. And I think some of them were very close to doing that.
Right. Louise, go ahead. Do you have a point?
I have a question for Ezra. When we were there, we saw a lot of the debris being deposited along the roadways and, you know, really being used as almost, you know, support, you know, to prevent landslides and further ideas. Do you think that was a useful construction? I mean, your point about an awful lot of debris, where do you put it, is a very good issue. But I just wanted to ask you about your assessment of that strategy.
Yeah, that's the first I've heard of debris being used to resist landslides. It's kind of an interesting concept. I suppose theoretically it could be helpful. If you have soil that's very vulnerable, that is easily liquefiable, and slopes that are pretty steep, but I would generally think you would try to get the debris out of there and maybe have some engineered structure if you're worried about things like landslides. You don't want to block all the roads with debris.
Well, they were alongside the road, so it didn't block the roads. But you know, and the hills in that area are not really steep. They're more rolling hills like we see here in Northern California, very large hills. But that was the rationale that was given to me when I asked about it.
Interesting.
Basically, it seemed like they had to put it someplace.
Yeah, there were massive traffic jams to get to the debris sites as well. So yeah. I'm sure a lot of people just wanted to unload debris and then get back into the city, collect more.
That's a great point. Ezra, I want to follow up on Uzgur's question. I think first one, he mentioned vertical ground motion. About the walking out of the girders, out of the rubber bearings. So was that area that you saw those kind of damage was close to the fault? It was counted as near fault or not? That's my follow-up question. And do you think those like big inelastic residual deflections that you could see in on the piers or those walking out are related to the sequence of ground motions, two big ground motion that happened back to back?
Where the rubber bearings did walk out, those typically were in near fault locations, sometimes within a couple kilometers. So as near fault as you get. And the residual deformations, I mean, a residual displacement, it's really hard to predict with an analytical model. And it's always a function of the earthquake sequence. When you have a large earthquake, though, and your structure performs inelastically, or you have some sort of soil failure, though, then it's a safe bet that you're going to have some sort of residual deformation in one direction or another. Occasionally, you get lucky and you end up back at zero, but that's pure luck. So when there's intense shaking, soil failures, you can expect some residual deformation.
Sure. Yeah. Did you have any access to the documents of the poles or the substation or those kind of, because they look so old. You mentioned, you showed the like a small rebars in those areas. They look like old facilities being built by very older codes. Did you have any access to those documents about the ages? Even the bridges for Hatay Bridge, do you know what is the age of that bridge?
So on the electrical side of things, no access to drawings. I think the substation buildings vary in age, and some of the newer ones are actually being built in pretty similar ways. There was one site we went to, and they had just built a new substation a year ago. It was right next to an older one that was still standing, and the older one, interestingly, performed pretty well. And the new one had a whole bunch of masonry infill that fell on the equipment and was no longer functioning. And the old one wasn't functioning either, so they set up a mobile substation next to it. So my sense is that the construction is not wildly different. Certainly architecturally, they still have these double height structures without a solid slab providing any sort of diaphragm action halfway up the structure. On the bridge side of things, we don't have drawings for a lot of them, but we've been able to get measurements both from in the field when rebar or when concrete spalls, and you can measure reinforcement as well, which is quite useful for numerical models afterward.
I have a follow-up question on the bridges. Are they too different from what we have in the US, especially in California, in terms of design?
I think, yeah, the lack of diaphragms is certainly quite different.
Okay.
I mean, you obviously will see shear keys resisting transverse movement in the US. I don't think that the provisions for that are actually in AASHTO. It often falls to state codes and other standards for how you design and detail things like that. And then the bearing, just a flat bearing pad that's not keyed in to pier caps at all is maybe a bit unusual, but not completely unheard of.
Okay, so you would expect probably better performance here in California.
Yeah, and I want to answer yes to that question without the point being lost that I don't think the performance of the bridges in Turkey were completely horrible. And they were subjected to incredibly intense shaking, many of them older bridges, and for the most part they did pretty well. And many of them, even while being damaged, were still functional. So I don't want to say that the performance was completely unacceptable.
No, for sure. No, for sure. I think, yeah, especially compared with buildings, I think, yeah.
Yeah, exactly. Yeah, you have to look at the context too. And I mean, there are fundamental differences between bridges that are built by government organizations that are much more likely to have robust inspection programs than older buildings that perhaps in some cases are non-engineered, or when they are engineered, don't have the same construction quality standards that we might have elsewhere.
Definitely. Thank you so much.
Following up with actually with Gloria's Ezra, was there any other like steel bridges also? What any damage or any cable bridges in that area?
I don't think we saw any cable stayed bridges. We did see a couple of steel bridges, and often the facades on those steel bridges had damage, or a piece of the facade fell off, just exposing the steel that you couldn't see before. In one example, there was a soil failure near the end of the steel bridge, and so the deck had lifted up and moved a bit. Fortunately, the soil sort of moved inwards rather than away, so the bridge didn't collapse. But largely, there were not a lot of steel bridges. Most of the bridges were like the ones I showed as examples, precast concrete elements.
Great.
If I may, I'd like to respond to Maria's question. Is insurance in general a successful strategy to force or encourage people to pursue a proper approach? Interestingly, one of the major changes after the 1999 earthquakes was that Turkey adopted a national insurance plan. Everyone had to buy insurance, and this was just, it was like tax, right? Everyone had to buy the insurance. So that insurance plan gave people a false sense of safety. The difficulty, the insurance plan didn't provide any requirements. Usually insurance plans here say if you want fire insurance, you have to do this, you have to have an inspection, you have to meet these requirements in order to qualify for the insurance plan. The Turkish National Insurance Plan was basically like a shared loan policy where you contribute to it. If your house building is damaged, then you can submit a claim and get reimbursement, but you then are responsible for rebuilding, repairing the insurance on your own. And it was nowhere near enough to cover the cost of the building. So, I think judgment is still out on the success of that policy. Literally everyone had subscribed to it, but then one has to make claims against it, and how are those claims being administered, and whether or not the money that is available is sufficient to help people rebuild their house. So it's a real question how effective that plan was. Could it be more effective? Yes, I think it could be, but I think it would have to be designed much more carefully and with requirements for qualification, included in the contracts, and then of course, administered much more effectively.
Thank you, Louise. That's very insightful.
Yeah.
Another question for Ezra. Can you comment on damages to underground lines?
I wish I could, but I can't. I'm sorry.
Another question is if actual code show a good response during this earthquake, or do we need to make changes to our code, especially in the soil side?
Yeah, I think that is a bit of an open question. We saw 90-some bridges and other teams saw more, and we are combining databases. And to me, whether there are code changes is a question of were there systematic problems, particularly when it relates to soil or intensity of shaking. And I think use of those databases to understand what the common problems were and how they tie to intensity, right? Was this just a 1 in a million year earthquake that you can't reasonably design for or not? I think it still is going to take a little time to get a satisfying answer to that question.
Right. Yeah. Great
As a
point.
non-engineer, I'd like to respond just based on some of the comments we heard from people. We did talk with one woman who had rebuilt a major building that was actually a solar power transition station. And the difficulty was they had done everything right, they thought. They'd gotten the soil assessment, they'd gotten the building codes, they'd gotten the qualified engineers, and it still collapsed. And the reason for the collapse was apparently the soil structure under the building. And so it was really more a geotechnical question and how to design that structure. But it was a major investment, relatively new, I mean, just maybe 3 to 5 years old. That was a major question.
Sure. Yeah, that was a great point. And always our codes are ahead of our construction. We don't need to forget that all of the buildings that are already constructed are mostly based on the older codes. So our engineering knowledge is just a little bit ahead of that. We have one more question. Why the historical buildings are not much discussed in this kind of discussions, and if the reconnaissance team has observed, has any observation on the historical building?
I don't know, maybe Louise, you might have a better answer.
Well, I would,
Lifelines primarily.
Again, I'm neither an engineer nor an architect, but we did talk with people from Antakya, and they were really, really sad and troubled by the fact that their historical buildings, some dating back, thousands of years, had been damaged. And there was a very special museum in Antakya that housed some of the really the treasures of the region. And there had been apparently a request, a special request made to that museum to check its structure and its design to see whether or not it could withstand an earthquake request. And apparently the director of the museum was about to retire, and he said, I'm going to leave that to the next director. Of course, the earthquake came, and this museum full of ancient treasures was heavily, heavily damaged. And so it's a big question. And it does go to, how does a nation preserve its history? And how does a nation preserve the artifacts that are really part of its culture? And this is a hard question. It does require investment, and it does require people who care about it.
And to follow up on this question, I saw there were some reconnaissance teams that focused a little bit more on historical buildings, maybe not from EERI, but from other international efforts.
Exactly. Also, we have some guidelines and standard for rehabilitation of the historical buildings. So it's not like that engineers just leave it out for architects. So we do have hands in.
I also want to say the German, there's been a number of German architects working with museums that have been very interested in Turkish artifacts. And I know that one group from Germany did go to Antakya and looked at that situation. I don't know what the outcome was, but the argument that the Turks from Antakya have said is this is an international, a world heritage. So it should not fall just on us. The whole world wants to know. And I would certainly share that assessment.
Sounds great. Thank you so much, Louise, for joining and supporting fifth Ishihara Colloquium. Thank you so much, Ezra and Kate Miyamoto. I appreciate every participant. I will hand it to Gloria and Elizabeth.
Yeah, thank you. Thank you very much for this great discussion. I really enjoyed this very live discussion. I think this was great. Thank you for all the participants. This is all from the San Diego chapter. Elizabeth, do you have any? I think, yeah, you sent a few links in the chat.
Great. Yeah, so thank you again so much to the San Diego chapter for organizing this this colloquium series. To those of you who joined us in the audience, and especially to our speakers. We will be sharing the videos of these 3 sessions on YouTube, hopefully sometime in the next week or 2. So you can check out them there if you want to, if you missed any of the sessions and would like to watch the others, or you want to share them with folks. And I also just wanted to note, following on that last discussion, that we are hoping perhaps to do a webinar either later this year or early next that actually focuses on some of those questions of cultural heritage, damage to traditional architectures in these earthquakes. So stay tuned. I'm just going to share my screen again briefly for a final slide. Oops, right through to the end. So first, I just wanted to thank everybody again for attending, and note that there will be a post-webinar survey. This should pop up in your browser, but you'll also get it by email tomorrow. So we'd really appreciate it if people could give us feedback. That helps us better design webinars to meet your interests. We will be having another webinar on November 14th that will feature a new tool developed for use by our public health reconnaissance subcommittee. That's part of our Learning from Earthquakes program. And some folks actually have been trialing that in Turkey in the field over the course of the past year. and we'll get to hear a report back on them. So for details on that webinar, you can stay tuned, check out the upcoming Pulse newsletter and the EERI website for more information and a registration link once that's ready. You can learn more about EERI at our website and donate to the LFE endowment that supports that reconnaissance work. And then finally, I just wanted to note that this webinar is supported by funding under a cooperative agreement from FEMA, as well as by EERI members like yourselves and the LFE Endowment Fund. Thank you for joining us.